Welcome to Raptor Networks. I'm Tom Wittenschlager, Chairman and CEO. I'd like to tell you a little bit about what we believe is the most exciting technology development in network switching in more than 2 decades. Have you ever wondered why it is in the computing world, when you think back 30 years and all that existed were mainframes, have you ever wondered how, given that computing has now fully evolved to the edge or fully distributed in the form of laptops and PCs, and the same thing has happened with storage. Storage started massively centralized and is now fully distributed. Does it strike you as interesting that the same thing hasn't happened in networking? Well, it hasn't happened up to now. But what's unique about Raptor Networks is Raptor has done in networking fundamentally what the PC has done to the mainframe. And that is we have developed the world's first and so far only fully distributed core network architecture. Well, let's talk about for a second what that really means. Let's go to a diagram here real fast. If you had 2 traditional chassis switches, and let's say you're sending traffic into port 1 here and out port 96, what does that traffic pattern look like in the OSI stack? Well, kind of simple. You come in at layer 2. The destination port is not inside the chassis, so you go up to layer 3, the processor. You discover that port. The port responds. The processor directs the switch chip in this chassis to send the data, which it does, transmits across to the management unit here, down to the switch chip in the destination chassis, and out it goes. That's called core switch to core switch traffic adjudication. This is the single most significant cause of latency today in traditional switch architectures. And as you know, under load, these latencies can be in the milliseconds. What's different with Raptor? Pure and simple. We do the same thing. We come in port 1 here, out this switch. The difference is, when you connect 2 Raptor switches, they bind and they become the same physical switch, even though they may not be in the same physical location. What that means is every port in this network sees every other port as though it's inside itself. Implication, we cut through route at layer 2, not in milliseconds, but in 4.58 microseconds. So what's the first element of our value proposition? Speed, 100 times the speed performance of traditional chassis-based architectures. If we have 4 chassis-based switches in a mesh, and this is very typical of a cross-town connection, cross-campus connection, mini-metro environment, multi-building interconnect. 4 big chassis cross-connected on 10 gig E in a mesh. As you know, if we make this link active, this link active, this link active, this has to be passive. The reason is if you allow a loop to exist, what will likely happen is a broadcast storm may bring down your whole network, and that's unacceptable. Well, if this is active, 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 passive, that means this can be active and this must be passive. The implication here is kind of staggering. You've paid a lot of money to put these links in place. Typically they're fiber, they're XFPs, and yet you can't turn them all on. And the reason you can't turn them all on is a limitation of traditional centralized chassis architectures. That's an issue. In a Raptor network, in exactly the same topology, same scenario, same everything, remember that when we connect 4 of these switches, they actually bind and become the same switch. What that means is every link that you've installed and paid for is in fact turned on and active. Very different from here. So the transport capability across an equivalent architecture, all other things equal, is at least 20% better. So in our architecture, all links are active, and as a mean, you basically get 20% greater transport capability across an identical topology. We think that's a pretty big deal. In every architecture, you have a master. The master manages the entire cluster, if you will. Raptor has a master, no different from a traditional switch architecture. The difference is the average failover time in a typical chassis-based environment is 45 seconds. Now, in 45 seconds at line rate, you're going to lose about 1.5 trillion packets. Now, what happens in a Raptor architecture? Well, let's look at the product real quick. This is a Raptor ER1010. This is our flagship product. Now on this ER1010, you will notice that we have a midplane. By the way, the capacity of this midplane is 160 gigabits. We have our switch chips, which are Broadcom Strata XGS2 series silicon, and we have our management module, which is a Motorola PowerPC 8541. Now what's different in our architecture is when we connect these over fiber or copper, what we're really doing, we're not stacking. We're making a common connection between midplanes. Very, very different. So we're virtualizing a midplane across physically separate machines. Now what that means is the master image file in the master with every heartbeat protocol is in fact replicated everywhere else in the cluster. If that master were to suffer a casualty, the next inline master picks up in 2 heartbeats. The distinction is, while the next master picks up, every switch continues switching. There is no packet loss. So failover, 2 heartbeats, packet loss, 0. Welcome to the Raptor Test and Integration Facility. I'd like to show you where we test our equipment, where we pre-configure it, where we make sure that everything is operating properly, and then prior to shipment, configure it for our customers. Nothing is harder for a network to transport than video, whether it's video multicast, streaming video. You know, who told our competitors that switches had to be large, heavy, uninspired, ugly, and traditional? Here's what we think it ought to look like. 12 pounds, 160 gigabits, transportable, wire speed, non-blocking architectures. This is what the future looks like. This is what the past looks like. You wonder why people get attached to this stuff. Up here, you'll note fiber spools. Each of these fiber spools are 20 kilometers in length. We can connect these between ports in a 1010. This is how we simulate connections of up to 80 kilometers. We ensure that over those distances the connections work, and of course we test them all on an Ixia tester that'll provide an aggregate transport capability at a given latency. It's been well tested in the lab, it's been shaken out. We've transported multiple streams of video over it so that when we ship it, we know it's going to work exactly as we said. In many environments, you have the need to stay connected to the network at all costs. The way that's done is you take a network interconnect card. In this case, we're showing a 2-port NIC card, PCI interface. You simply plug this into your server, your device, your sensor, and now you have 2 ports or 4 ports or 6 ports with which to connect to the network. Now, in a traditional network, what happens? Well, what you do is you set up your device with your multiple NIC cards, multiple port NIC cards, and you go ahead and you run these RJ45 connections up to a chassis. Now, in every traditional architecture, for link aggregation, or IEEE 802.3AD, to function, you can only aggregate these links in a common chassis. More often than not, you can only aggregate them on a common blade. Now, that's great if you lose one of these links, you're still connected. It's not so great if anything happens to that chassis. If anything does, basically you're toast. Now in our architecture, very, very different. Remember that these 4 physically separated machines, when connected, in fact bind and become the same machine. What that means is you can send your links to separate physical machines in the cluster, and link aggregation still works. Now the scenario is entirely different. For you to be disconnected from this network, this machine must fail, this machine must fail, this machine must fail. Literally every network switch to which you are connected must fail. Radically different definition of redundancy, radically different definition of assured connectivity. So aggregation is now possible across separate physical devices. And reliability that results from super redundancy is out to the 6 or 7 nines range. Nobody ever thought that was possible before in network switching. It is now. A thing that a lot of people worry about when you have such a revolutionary technology is the question of, do I have to throw everything I already own out? And that's a valid concern, because people may have spent millions upon millions of dollars on a network or core switch architecture and then discover that, wow, I could have in fact put in a distributed architecture that's faster, more efficient from a topology perspective, more reliable, more redundant. Well, not to worry. Outwardly facing, this revolutionary technology is fully open standards compatible with everything out there. Said differently, you can think about this technology in 2 different ways. If you're building a new network, this represents the highest performance and the lowest cost available anywhere today. If you've already installed or have installed a major network, you could think of this as a giant coronary artery bypass around a traditional network, establishing a secondary data path. Let me show you what it looks like in practice. LA Care, one of our customers, is the largest public HMO in the country. They manage Los Angeles County's healthcare system. Now, they had a pair of traditional switches from the industry leader, and they kept adding employees, and the network finally became overloaded and couldn't take any more. They went to the industry leader and said, hey, what's it going to take to upgrade these switches? Well, let's talk about what upgrades mean to our competitors. What an upgrade to our competitor means is replacement of both power supplies, replacement of both management modules, replacement of the backplane, and even replacement of the fan tray. Long story short, for LA Care, upgrading the core switches that they had already purchased meant a $500,000 or a $500K bill to give them a 10 gigabit transport backplane. That was until we showed up. We suggested, hey, take 4 of our flagship ER1010s, connect them in a mesh, now cross-connect our topology both ways to your existing products. What did it mean to LA Care? It meant they had to throw nothing out, they had to replace nothing, they had to rewire nothing. They simply had to add 4 switches and cross-connect them to their existing architecture. Here was the value proposition. This is what the industry leader offered them, $500,000 for a 10 gig backbone. We offered them a 30 gig backbone for $100K. So you make the call. 500K for 10 gig or 100K for 30 gig. Needless to say, we're installed there. We have been installed there. We've been operating for more than a year and a half. We've had a flawless performance record. We have a happy customer, and more importantly to us, we have a repeat customer. They've purchased a lot more switches. Okay, so we are, on the compatibility side, fully compatible with existing traditional architectures, which means you don't have to throw anything out. Finally, on price. On our worst day, we're half the price of a traditional architecture. On a better day, we're a fourth of the price. That, we think, is a highly unique value proposition. And the reason we think that as a customer or as a partner, you should give serious thought to adding Raptor to your list of equipment is quite simply that with traditional architectures today that have been distributed now for almost 2 decades, from a distribution or from an integration perspective, there isn't a lot of variance, or there isn't a lot of differentiation on price or on performance. It's in the 10% or less range. Here we're talking about orders of magnitude difference in performance, a step down function in price. As an integrator, you can make significantly greater margins. As a customer, you can save 40% or more of your budget while dramatically improving your performance. That's the Raptor uniqueness. It's the Raptor value proposition. It's what we're very proud of. We'd like to welcome you as a customer.